Now we want to classify all the trigonometric identities so that it's easier for you to learn all these identities. You find that there is a whole set of trigonometric identities which we must learn before we can attempt the proving of identities. Now there are some easy ways to do that. Now for the first part, we call reciprocal identities. You find all these identities having 1 over a trigonometric function. 1 over a trigonometric function. So that's why we call reciprocal identities. Where we have 1 over sine x, then this identity will be cosecant x. Where we have 1 over cos x, your identity is secant x. So when we have 1 over tangent x, then we'll have cotangent x. Now these are all short form, like this. Short form for sine x. Of course, the cosine and the tangent so over here we have the cosecant, we have the secant and the cotangent. Now, it's easier to remember this way when you have the sine, which starts with an S, then you have a cosecant, which starts with a C. So if you have a cos, then it's starting with C, right? Over here you have secant, which starts with an S. So cotangent, tangent, they are a pair. So here 1 over secant x, you know because it starts with a C, you expect something to start with an S. So that will be sine x. So it's just a manipulation of this. You can see these two trigonometrical functions switch place. Here you have 1 over secant x. So the result will be cos x. Then 1 over cotangent x will be just tangent x. So reciprocal identities, 1 over, you have 6 of them, but if you just memorize 3, then you can derive the other 3 just simply by manipulation. The next group that we're looking at is the quotient identities. You can see over here, you have the numerator divided by denominator that we call quotient. So this group, where you have the algebraic fraction here, it will be reduced to just a singular trigonometrical function. So sine over cos will give you tangent x. And you can see here you have sine over cos. Here is just the reverse. You can recall that when we had tangent x, the identity for this is 1 over cotangent x. So similarly, by just manipulating this, where this tangent x switch place with the cotangent x, you have 1 over tangent x. Let's go further from here. According to what we have there, tangent x gives you sine x over cos x. So what I have here, the tangent x now is replaced by sine x over cos x. 1, if I change this divide to times, then this will be inverted to give you cosine x over sine x. You can see from here that the cos x over sine x really is equal to cotangent x. So for this expression, where you have also here, then you get cotangent x. So to put it simply, tangent x gives you sine x over cos x. Cotangent x will give you just the inverted form of this, which is cos x over sine x. Next, we have the Pythagorean identities. When we talk about Pythagoras theorem, if I'm looking at a right angle triangle, naming this longest side as C, then the other two sides, one I call A, the other I call B. With these three sides, you can relate them simply by C squared equals to A squared plus B squared. So the square of the longest side in a triangle is equals to the sum of the two sides squared, or the square of the two sides. So you can see this arrangement here, where you have an item squared plus another item squared. So we call this group Pythagorean identities because of an item squared plus another item squared. So that will help you to remember this very clearly. So when you have sine squared x plus cos squared x, you just get 1. And if you have 1 plus tangent squared x, then it will be secant squared x. And when you have 1 plus cotangent squared x, then you will have cosecant squared x. Now, if you look carefully at this again, every single term is squared. So you get cosecant squared, you get secant squared, you get actually 1 squared, which gives you 1. Lastly, we have the double angle identities. You can see over here, you have sine 2x, double angle. Cos 2x, double angle. Tangent 2x, double angle. So I would expect in the expression over here, the angular expression would just be x. So that this angle is double what I'm going to get. So sine 2x will be 2 sine x cos x. You can see this angle here, 2x, is double of that angle, x. For cos 2x, this identity gives you 3 parts. You can have cos 2x equals to cos squared x minus sine squared x. That is just 1. Now, we have another identities from the Pythagorean identities group, which is sine squared x plus cos squared x equals 1. Now, from here, we can derive the next two. So the next one we are going to get is 2 cos squared x minus 1. Let me just show you how this part is obtained from here using these identities. Let's start with cos squared x minus sine squared x. Now, in order to get an expression in terms of cos x, then what I need to do over here is to make sine squared x the subject. So I will transfer this to the other side. So from the left hand side where I have positive cos squared x, now it will become on the right hand side minus cos squared x. So sine squared x is equals to 1 minus cos squared x. I will take this expression to replace sine squared x. Here, you notice just a direct substitution, 1 minus cos squared x. Now, using the law of distributive law of multiplication, you have negative 1 multiplied to 1, negative 1 multiplied to negative cos squared x. So you have, because negative and negative gives you a positive cos squared x, you have a cos squared x plus another cos squared x. You get 2 cos squared x minus 1. There you go, you have this expression. The other one is just 1 minus 2 sine squared x. Again, let me just show us how we can derive this third one from this expression. Because we want the expression to be in terms of sine x, so we will have to make cos squared x the subject. So I'll transfer the sine squared x to the right side. So cos squared x equals positive sine squared x from the left hand side transferred to the from the left hand side transferred to the right hand side. This is what I get. So with this expression substituted into here, so just opening up the bracket, 1, and I have negative sine squared x plus negative sine squared x. That will give me a cumulative effect of negative 2 sine squared x, which is just that expression. Where you have tangent 2x, the expression is 2 tangent x over 1 minus tangent squared x. Well, just to talk a little about this one. Tangent 2x. Well, the other form is tangent a plus b. The formula is this: tangent a plus tangent b over 1 minus tangent a tangent b. But in our case, you have 2x. So what it means is that when a is x and when b is also x, this is what we're going to get: tangent 2x. And this a is replaced by the x. I have tangent x plus tangent b. The b is replaced by x, so I have tangent x. So I'll do the same replacement here. A is replaced by x, b is replaced by x. So to simplify it, tangent x plus tangent x is just 2 tangent x. And over here, we have tangent x times tangent x. So another way to write it is tangent squared x. That means the same, tangent x times tangent x. So in this section of the work for trigonometry, you realize that we will manipulate the identities to obtain other forms, other different looking identities. So this is the end of the segment.